Okay, so last time we were looking at the difference between strong acids and weak bases, and now we're doing the same thing with bases. And basically, these adjectives mean the exact same thing. So a strong base completely dissociates to produce OH minus, and a weak base partially dissociates or reacts with water to make that OH minus, right? So it's all about those arrows. Strong bases, we're going to see a full arrow. Weak bases, we're going to see that back and forth equilibrium arrow, right? So here's NaOH dissolved in water, and it completely dissociated. There's not one formula unit of NaOH, but when I put NH3 in water, some of it reacts with water, so we get some OH minus and NH4 plus, but for the most part, it just remains intact, right? And then how do I know whether bases are weak bases or strong bases? Well, we've memorized the strong acids. We do the same thing with the strong bases, that there are 8 strong bases. There's the 5 that are made with the alkali metal hydroxides, and then these guys, calcium hydroxide, strontium hydroxide, and barium hydroxide. I kind of think it makes a B, like this is how it looks on the periodic table, and it sort of makes a B for base. Weak bases, ammonia is the most common one, but these other ones are good examples too, but notice they all have nitrogen in it. Nitrogen often is in weak bases. And again here, you see the arrow fully to the right for completely dissociated, and then the equilibrium back and forth arrow for weak bases. So this question says, determine the OH minus concentration in basic solutions. So I have to look and see, are these strong bases or weak bases? KOH is a strong base, so it completely dissociates into K plus and OH minus. So if it's 2.25 molar KOH, it's 2.25 molar OH minus. This one right here is not a strong base, it's a weak base. So there is a number, and we can figure this out, but not this year. So we would say we can't know that right at this time without more information. For strontium hydroxide, strontium is a 2+ ion. So when this formula unit dissolves and dissociates, it's going to produce twice as much hydroxide. So it will be 0.025 molar in strontium, but it will be 0.050 molar in OH minus. And since this is what is determining the basicity, the alkalinity, another way to say that word, and the pH of that solution, it's really important to notice that that there's 2 OHs in this. And as I said, why is that important? It's important because we use this to calculate pH. Basically, pH, it's a lowercase p, capital case H, because the H is standing for hydrogen. At 25 degrees Celsius, and temperature does matter, that a neutral solution, an H plus and OH minus are both the same. They're both 1.0 times 10 to negative 7. That's not very big. In order for a solution to be basic, it has to have more H plus than that. And in order for a solution, I think I said basic, acidic, it has to have more H plus than that. And for it to be basic, it has to have less H plus than that. And this is graphically showing you that there's always some amount of OH minus and H plus. It's just whatever there is more of is whether it's an acid or a base. So even in a basic solution, yeah, there's going to be some H plus, but there's going to be way more OH minus. And neutral is when they're both exactly the same. And so the further away from 7 you get, the more acidic or the more basic the solution becomes. So you could see if 7 is right around here, right? You get things that that we interact with on everyday: rainwater, human blood, right? Beer, cherries start to get pretty acidic. And all these, here are some citrus fruits that we know are quite acidic. And then stomach acid, very strong acid there, very low pH. And then these, remember ammonia we talked about as a cleaning solution? Its pH is around 10 or 11. Milk of magnesia is something that you might take if you have an upset stomach. So if you have more acid in your stomach than there typically is, milk of magnesia will neutralize that acid and make you feel better. And the actual scale of pH is a logarithmic scale. So each time we get the exponent, right? Logs are exponents, exponents are logs. Each time the exponent changes, it changes how much acid is present by a factor of 10. So when I go from a pH or an OH pH of 4 to a pH of 3, I actually increase the acidity by 10 times. And when I go from 3 to 2, I increase the acidity 10 times. And so here's the actual formula. pH equals the negative log of the H3O plus, or remember, those two things are synonyms for each other, H plus concentration. And then here it is going the other way. If I have the pH, what is the H3O plus concentration? So if I take a look at these solutions right here, right? This says calculate the pH of each solution and indicate whether they are acidic or basic. So all I'm going to do here is in my calculator, press the negative button, press the log button, and then 1.8 times 10 to negative 4. When I do that, I'm going to get 3.74, and so that would be an acidic solution because it's less than 7. I do the same thing over here. The negative button, the log button, 7.2 times 10 to negative 9, and that is going to come out to be 8.14, which is a basic solution, right? Remember, we use that small but uppercase E to do those exponents there. And then if it is an strong acid, remember we said strong acids completely dissociate. So whatever is the concentration of the HCl, the concentration of the H plus will be exactly the same. So the formula for pH is the negative log of the H3O plus, which is going to be the negative log of 0.00356. And that comes out to be 2.449. And this one is going the other way around. So the formula is 10 to the negative pH is going to be equal to the H3O plus concentration. So 10 to the negative 2.19, and that comes out to be 0.0065 molarity, right? Because it's the concentration. Oh, by the way, brackets around something means concentration in terms of molarity. The concentration of H plus is, or H3O plus is 0.0065. And yeah, we do have to add the unit of molarity on. pH has no unit. So it's not that this has a pH of 2.19 pHs. It is unitless, so it doesn't have a unit.